Hello, everybody.
Hi.
If I might. Hi, hi. So my audio's on. Is my video is probably on? Is that right? Yeah, looks like it. Oh gosh. How's everybody holding up? So? That's good. That's good. You guys are strong. Conquering the world. It's a lot to conquer. Let me see. I'm going to make room for more of you here. I have an enormous television in my office. I wanted to get a large monitor for my laptop in my office, you know, and by far the cheapest option was to buy a television, just like way cheaper. So I have this huge TV. It's about this big. So for me, this is just like watching TV. But can you guys see Ernest, Hans, and Ernest? Okay, cool. Good. Excellent. I'm just waiting for a couple more folks to show up, then I'll start blabbing away. I got my coffee coming. Can you see my coffee brewing in the background here? It's my afternoon coffee. It keeps me awake at night, though. I didn't go to sleep till like 1:30 this morning. Bad news. I get up late. It's terrible. So I realize that I am trying to blast through everything super quick, and I'm doing everything a great injustice. Would you guys agree with that? Sorta, maybe. Like, for example, this whole business about, there was old Ernest who, they discovered that the alpha particle was helium by putting alpha particles in this little tube and then letting them, it was just like a 16 micron thick tube or something. You got a glass blower to blow a really fine tube. And then they had, I'm not sure, I couldn't quite gather whether they had radium actually in the tube or whether it was all xenon, like, because they called them radium A, radium B, and radium C. That's radium and the daughters of radium. You know, that when it decays, it creates a new thing, and that decays creates a new thing, a decay chain. And down the decay chain, a couple steps from radium is xenon, you know, and xenon's a gas, right? So I'm not sure whether they had actual radium in here or whether the tube A was just filled with xenon. But the alpha particles that the xenon was shooting out could go through the glass, you know, and they established that using glass barriers and alpha particles and a detector, you know. And so they knew, oh, the radium C alpha particles can get through glass, right? But the glass can stand up to atmosphere. So that was actually the words they used in the paper, that it can basically hold the gas in. You know, the gas doesn't leak through the glass, but the alpha particles can fly through it. So and then what they would do is they would compress after they let this go for a day or 2 days or 3 days. They would this hatch stuff in here. This is mercury, you know, and then they would raise this thing, and that would push more mercury in, and the mercury would compress the gas up into this tube here, and then they would set up an electrical emission in the tube, and that's how they could tell if it was helium or hydrogen or nothing, or right. So I thought that was pretty clever. You know, that was an interesting example of turn of the century sort of physics, you know, and it's really interesting. Like, I didn't really understand the point, for example, of what all these valves and stuff were for. But this tube F here, that's filled with charcoal. They had some sort of a roughing pump, I think, that they could connect to D here, some sort of piston pump or something. But then they would close that off, and then they would open it to F, and they would freeze F in liquid air because they knew how to make cold liquid. That was one of Kelvin's contributions. They could make liquid air. They could compress air and expand it, compress it, expand it, and in the expansion chamber they could condense liquid air. And so they would put charcoal in here and then freeze it in liquid air, and then that would condense all these gases out, you know. And so this F is our high vacuum pump. And the way they opened their high vacuum pump to this chamber was they just lowered the mercury. They just got the mercury level way down there, and then they opened the stopcock, and whoop, they could evacuate it. But anyhow, so my question about this was I doing things justice or not, you know? Or was I just blowing past things too quickly or not explaining them enough, you know? So and we moved on from there real quickly to talk about distributions, right? Because the alpha particle helium and argon were almost co-discovered. But argon was discovered in a different way. It was discovered by by Lord Kelvin and William Seeley Gossett, you know, and I just cannot. I mean, can you just see these guys having a beer together in a pub? I mean, I can't resist that. It's just so funny, you know, like he's got such a goofy face. He looks like Wallace and Gromit, you know, he looks like he was one of those. It's just so funny. But then I sort of blew past that into statistics, right? And how many of you understand what this blue line is supposed to depict? Let me just sort of throw that out there and see. So this is the mass line. This is the mass of the gases that they collected from these two different processes. And nitrogen was a little bit more spread out than air, but if you put these data into a spreadsheet and you generate the histogram, then you get these distributions. Does that make sense? So Caleb is saying yes, he kind of understands. Lucas says yes. I would like someone who doesn't quite get it to be courageous enough to tell me what the, like, where that train goes off the tracks, if that's okay, if you feel like it. Well, yeah, I guess if you feel like it, right? So what, for example, let me first do a nice way. Now I'll be bad cop, good cop, bad cop. So what is the vertical axis on this blue plot?
The volume.
No, it's not. That's good.
The
So
amount?
on the blue, no. They're kind of like, you're kind of like getting there, right? But actually, this is the probability.
Like math, where it's like how much it deviates, kind of like the
Okay.
one on the left is more spread out.
Excellent point. So the deviation is on the x-axis, right? And the peak of this is on the mean. And then the width of this is the deviation. And the vertical axis is actually probability. The probability that the mean of this distribution lies here is highest, right? That's at the average of that distribution. Does that make sense? So I would like, so I'm going to ask again. I'm like a friggin' broken record here. For whom did that kind of go off the rails? For whom did that, like, okay, I was getting it, but then he said that was probably, so Maximus. Yeah? And Kita, good, excellent. So what is the probability that the mean of these points is 2.315? Low, exactly. Maybe even 0, right? Because the points are over here and their average is here, and the mean is the true central tendency of that distribution, right? It's really where the points are going to collect around. And we have this limited number of points. And they collect around the average so far, you know? And so if we take more points, will the average change, Brian? maybe?
Yeah.
It'd probably shift a little bit.
Yes, yes, it will. It will. And somebody said it'll probably shift a little. Why not a lot?
Well, it just depends on the samples collected.
Exactly. Exactly. It's like, what are the chances that the first 10 points were just all outliers in the same direction? Just by the random chance. They're all like, it's like all of the air moves to the left side of the room by random chance. It's just so improbable, right? So this vertical axis is the probability that the mean of this is the population that made these points, right, is here. Yeah? Does that make sense? Better, maybe? Okay, I got some thumbs up, I think. That's good. That's good. Okay. So why is this probability distribution broader than this probability distribution, Emma? Not sure? All righty. Celine?
I'm also not sure.
Okay, good. So I could be asking, why are these points farther apart? But I'm not. The points are the experimental data, right? And they're just what the experimental outcome was, right? And none of them are, no point is perfect, right? They all have some uncertainty. But their average is right here. Yeah. And so because these points are more spread out, their probability distribution is broader. Right? So which of these two distributions has a larger standard deviation? The nitrogen from air or the chemically generated nitrogen?
It would be the chemically generated
Right.
nitrogen.
Chemically generated.
Right. Exactly. All right. So if that's not clear to you, then we should take some time to get it clear, right? Because the standard deviation is the breadth of this distribution, right? Okay, here's another question. Here's another question for you. Why is this one the same shape as this one, even though these points are more spread out than these points? That's a trick.
Because they're still
Complete.
clustering around the mean.
Yeah, who said that?
Sedona.
Wave your hand. Ah, Sedona, thank you. So, okay. These points the way they're drawn here, these points clearly cluster around a mean, right? But these guys, there's 2 over here and there's like 6 over here or 5 over here, right? So you could say that these don't cluster around a mean, right? But the way we're modeling them, our hypothesis is that these all belong to the same distribution. And what that means is if we were just to keep hammering on this experiment and the laws of physics stayed the same, then they would eventually make a pile with a peak right around here, right? So that's really our projection onto the experiment, right? It could be that these were done by Harry and these were done by Sally, right? In which case we might change our hypothesis and say, no, the Sally experiments are over here and we'll get one bleep over here and one blop over there, right? But that's not what we're doing. We're saying that these are from chemically generated nitrogen and they are of the same population, yeah? And these are nitrogen from air. Yeah? Better? Good. Okay, cool. Now, I have got a shit ton of real estate on my screen, but I still can't quite see everybody. Who knows how to fix that? Let's see here. Oh, and I got to get to the chat. Oh my gosh, I see the chat. Chemical, normal is true. Okay, I am so sorry. I was not reading the chat. Maybe it's better. But so let's see here. I'm trying to participantes. No. More. Shoot, they were telling me there was a way that I could see more of y'all on the screen. That's okay. That's okay. I'll kind of toggle.
If it's not already on.
Sorry?
I think you can change it to gallery view.
Yeah, I did change it to gallery, and I can see a ton more of y'all, but I still can't quite see all of you. And there's just a bunch of black space above and below, so I can see like I can see 25 people. But you're supposed to be able to see 50 or 49 or something.
If you go to video settings, you can change it to 49 people.
Okay, video settings.
So where it says stop video, there's like an up arrow. If you click that, and then scroll down.
And scroll down to 49 participants. Yes! Thank you. Yay. I can see all of you. I think. Yeah, I can see everybody. Okay. So, and basically you can do all this. You can, once you have this framework, right? That these are from the same population, these are from the same population. You can ask the question, what is the possibility or the probability maybe that these numbers and these numbers come from the same population, right? And it's just because by whatever chance, these guys came out over here, and these guys came out of there, and the real distribution is something like that in between, right? Something with a mean around here, right? Something like that. You can say, okay, there's this and this, or there's some broad one in the middle, right? You can now ask that question and get a quantitative answer, right? And that is the essence of probability theory right there, right there. And nobody's going to tell it to you the way I do. Nobody. I guarantee it. It's all going to be gobbledygook. So anyway. Or maybe I should say gobbledygookier. So somebody asked me a question about this data that's somewhat intelligent. Or somewhat stupid, actually. That would be maybe better. Okay, no questions? Okay, so I'm going to assume I beat this horse to death, and we'll let it germinate in our minds. Rohan, you have the most ominous background because your background is
Yeah.
completely black. It's like you're in deep space.
Yeah,
You're coming to us
background
from
is just a mess, so I changed it to black.
ah.
My actual room behind me is a mess, so I didn't want anybody to see that.
Oh my gosh! Oh my gosh! Oh my gosh! That's okay. That's okay. I just wanted to say, it's kind of funny. Okay, so then blah and blee, and okay, so here we are today, right? These three guys did a very famous sort of physics experiment, right? They used a gold foil. How many of you have heard of the gold foil experiment? Show of hands. 1, 2, 3, 4, 5, 6. Okay, so probably most of you have heard of it, right? All right. So of these three guys, you know, it's basically Geiger and Marsden did this in Rutherford's lab, right? Now, who can tell me which of these three men turned out to be a Nazi?
Hans.
Hans Geiger.
Yes, it was Hans. You can just see it in his face. He looks like an evil genius or evil something, right? Evil scientist. He was a pure Nazi in World War II. I mean, he was an old guy by then, obviously, but he joined up with those National Socialists and carried that banner. Anyway, so so let's just watch a video then about the gold foil experiment. This picture I do not friggin' understand, so forget it. But let's watch this. Let's watch this experiment here. Come on. Oh, there we go. There we go. Come on. Gold foil experiment. YouTube. You guys have to tell me whether or not you can see the. Okay,
We
go.
can see it, but I don't think it's sharing sound.
Okay.
Yeah,
I don't know
I
how
can
to
see it,
share
but I
sound.
can't hear it.
Okay. It's how do I do that?
I think if you go on to the thing on the top of your screen where it's like you're sharing your screen, you should
Yeah.
be able to press view
Yeah.
options, and then from there it should say like share audio or whatever.
Okay, on video settings, maybe?
I think it requires stopping sharing your screen and then starting again. And then at the bottom of like the white pop-up menu, it says share computer sound. I think that's how.
Okay. Okay, so I stop sharing. Okay, that's new share. And then I can say, wait, no. You are screen. Oh, stop share. And then what?
And then try sharing your screen, but before like you actually click share screen, it's the pop-up menu that shows like the different windows. At the bottom of that, it should
Uh-huh.
check mark that says share computer sound.
Okay, all right. So I go to share screen and then I have, oh, and then I use the whole screen rather than the window. Is that right?
I don't think that
Possibly. Oh, share sound. There it is. Share sound. Yeah. Thank you. Excellent. Cool. So here we go. And I apologize that it's like so messed up in terms of like all this crap around it, but I'm afraid if I full screen it, let's see.
Heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil.
It just got infinitely smaller for me. I don't know if
Oh, there it is.
That's too
How-
funny. Oh,
better?
there we go. There we
Okay,
go.
good, good,
Yes.
good, good.
Mission
Okay.
accomplished.
Now, where's the sound? Oh, wait, I got to start it to play again. I'm going to go back. Okay, going back, going back.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology.
That's their modern technology.
Behind the foil, it will measure one count every few seconds.
Bingo! Hello!
As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
Okay.
What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
So, one thing that this guy knows is not true.
Kid.
Oh!
Said to take you back to the
Oh my God! Have you guys seen this? I really enjoyed this series, but I'm letting go of this stupid subscription because there's been nothing good on Disney for a long time. But anyway, so first of all, does anybody have any questions about that or any observations or anything like that? No. Too boring. So one thing, this guy misspoke in the way that everybody misspeaks about this. And he said that the alpha particle hits the gold nucleus, but that never happens. It never hit, the nuclei never, because the helium nucleus is bare, right? It has 0 electrons. It's 2+ and it's cooking, right? And it flies into the gold, and it, you know, I'm sure it interacts with the electrons, but not a whole bunch compared to its energy, right? And then, but then what happens is that the nucleus comes into the electric field, or the alpha particle comes into the electric field of the nucleus, right? And it's deflected by that field. They never actually touch, right? But the Large Hadron Collider is one where they touch, you know? And when they touch, depending on their energy, all kinds of shit breaks loose. And when they touch, right? You know, when they actually, when the collision cross section of the alpha particle and the collision cross section of, say, the gold nucleus, when they overlap, then if there's enough energy, then it creates jets of new particles. It just creates them. You know, you get quarks and antiquarks and huge numbers of particles, right? And that's particle physics, right? And it's funny because if you want to see that super tiny nucleus, you want to see how really small it is, you need a really high energy beam, right? Because if your probing particle, say your helium nucleus is too large, it's too low energy, it just comes and it goes, it never actually hits, it just, you know, it could sort of bounce off, you know. And all of the math that Rutherford did behind this, I don't really understand, but it's all geometry, right? And he had some interesting cases where, you know, the particle comes into this angle, goes off at that angle, you know, and it all kind of boils down to that. And but they're all just deflections, you know. You know, it's this 1/r² dependence of the force, you know, as it gets close. But if they get close enough and touch, everything goes to heck. And then at the particle colliders, you know, they use super high energies to see super small things. And the smaller you want to view, the more energy you need. That's sort of like one of the, I don't know, it sounds cool. Sounds cool to say it. And so far it seems to be true. You know, that like to see, like even with electron microscopes, the highest energy microscopes are like probably 50,000 volts or something, maybe 100,000 volts. I mean, if you look at them, they are these gigantic things. The power supplies for a TEM, they're gigantic. And they have this one wire that goes wow out to the top, you know, and it's like, don't get close to that wire because it's going to arc and you're going to die. But, you know, they have this power supply. It's just crazy, you know, and it goes to the top and it fires the electrons down. And then, you know, once you get this really high energy, really tight beam of electrons, then you can see atoms. Literally, you can see the electrons that make up atoms, you know. So, and I'm sure Xiaowei has shown you TEMs and things like that already, right? Yeah, no, I know he has. He likes pictures. Everybody likes pictures, right? Has he shown you pictures of atoms? Pictures of atoms? Yes? No? Yes? Caleb says yes. I think he probably has.
He showed us
Okay.
the formation of a buckyball today. Like
Uh-huh.
a simulation thing.
Oh, simulation. Right. Okay. Well, it turns out that, you can, so you guys are probably a little too old now. But if you had tried when you were in the 8th grade, you could probably take something to Evans Analytical and get a free transmission electron microscope image of your sample. And literally it would cost me $600 to get the same picture. But if you're in the 8th grade, you could probably get it for free.
Wait, why is that?
Because you're cute. When you're in the 8th grade, you're all.
Is that the only
What?
reason? Is there like, is it just because they
Yes.
take pity on you or something?
No. You see, you're in a weird age. You don't understand it yet, right? You don't see how humans evolve. When they're small, they're cute, so we don't eat them. And you guys are not really that cute anymore.
Ouch.
Sorry. I know. I'm sorry. You're growing up. It's part of life. You get smelly. It all goes to heck, right? I mean, so you go from cute to handsome and beautiful, let's say, right? Okay. Is that clean enough? Sanitized properly for you? But you know how little kids are cute, right? Like puppies are cute. That's how you get free TEM. You got to be cute. Because this little 8th grader came into my lab. Her mom brought her for a science fair project, and she wanted to make gold nanoparticles using curcumin and other spices, right? I was like, oh God. I mean, you could put tetrachloroauric acid in water and spit in there, and you would get gold nanoparticles, I guarantee, right? So she made them with curcumin or something. Took them to Evans, they imaged them. She got an A on her assignment, right? Because it looked impressive. Only because she had a $600 TEM. Anyway, I'm bitter. So, oh yeah, okay. So the last thing I'm going to talk about is the discovery of the neutron, because this was friggin' wild. And this, if anything, speaks to the importance of just doing shit in the lab. My friend Tosh used to call it hacking around. And you just do experiments, do whatever the hell you want to do. You don't write anything down. Ximing, do not listen to this. Xiaowei will kill me if he hears me telling you not to write shit down. You too, Davida, if you're here. But if you just do experiments, right? You can see that that's what these guys were doing. If you think about it, right? This is Chadwick. This is 1930s, right? They knew how to make collimated alpha particles back in the 1900s, right? They could make these beams. They would take these ultra hot radium sources and they would put them in a lead box with a little tiny hole drilled. And then that would make beams of alpha particles, right? So they would take a beam of alpha particles, blast it into beryllium, blast it into parafilm, and then blast it into a detector, right? Like this is just like all kinds of crap happening here, right? And they danced with the neutron problem for quite a while. And it's a funny story because Marie Curie, you know who she was, Jerry? Marie, she got 2 Nobel Prizes, one in chemistry, one in physics. pretty amazing. Like one of the very few people who's gotten that, right? And she was dead wrong about neutrons. Dead wrong. And Rutherford and his pals knew it. And they didn't tell her. She and Pierre, Marie and Pierre, they were basically doing this experiment. They found out that if you bashed alpha particles into beryllium, then it made a new type of radiation that was super penetrating, right? And they had no idea what it was, right? Because partly because you can't detect that radiation directly. You have to detect its effect on something else, like paraffin. Right? And I don't know how they discovered that. I think it was partly because there was some evidence like nuclei are heavier than the protons that make them up, you know? They're like twice that heavy, and it's like, what's going on here, you know? But they found out that you could have a whole bunch of air in the way here, and then put the wax, and it'll still create these high energy protons, right? Protons you can detect. Protons you can deflect with a magnetic field, right? You put a magnet in there, the protons they'll bend, right? So the alpha particles that came shooting off alpha particles shoot the beryllium undergoes a neutron capture. No, it doesn't. What the hell? It alpha captures, and then it emits a neutron, and then the neutron goes flying out. Neutrons are not detectable at this point, right? But if you put a piece of wax in the way, then what will come flying out of the wax are protons. Because the neutrons will smash into the protons, transfer all their kinetic energy to the protons, and the protons will be charged and they'll fly out of the wax, right? And up to that point, when people had been bombarding everything known to man, you know, hair, paper, whatever, with alpha particles, you know, from polonium or from radium, most likely, it just turned out that a couple of elements will produce neutrons, just a couple, right? And that was a major discovery, right? And there was some weird things like there's some weird anomalies, like if you have nitrogen in the air, then that helps. If it's carbon dioxide, it doesn't help. And so there was some weird stuff. And I'm sorry, I'm a bit vague on that, but anyway, that was Chadwick in 1932, and he was a friend of Rutherford's. You know, he was at McGill. That's where Rutherford was working at the time, McGill University in Canada. Why do all the Kiwis go to Canada? You know, Rutherford was from New Zealand, and he was a potato farmer. Shaming, do you know the answer?
I don't
Why
know.
the damn
I don't
Kiwis?
know about Kiwi.
I do not know why the Kiwis wound up in Canada. But anyway, it's just like opposite ends of the earth, right? Literally opposite poles, you know? Because New Zealand is like almost to Antarctica, and Canada is almost in the Arctic. Maybe they like the cold weather. But in any case, so detecting neutrons was not easy because you have to transfer their energy to protons and then detect the protons, you know? So anyway, so, oh, and then there's a beautiful set of transcripts of papers. Here, I'll put this on here. This is like all the history of science stuff. Come on, come on, come on. There we go. There we go. There's another link for y'all. And just a very cool unit on the history of science, you know, very, very cool stuff. Could talk for hours. Okay, so now this is the second major unit that we're going to chat about. And okay, so let's take a short break, right? Because I've been blabbing for almost 50 minutes now. So let's take a break until 2:30. It's 2:18. We'll take a break till 2:30, then we'll come back and we'll start with quantum. Okay. Bye. Let's see. Hey everybody. Let's see, is my audio is on, I think, right? Yeah. Good. Okay. So you guys want to watch YouTube?
YouTube's pretty cool.
YouTube's cool. You know, the guys that do YouTube videos, they spend weeks and stuff doing these, 20-minute segments. They're way better than I'm going to do. So let's listen to a YouTube on the Bohr model, right? And I think all of you are probably pretty well up on this stuff, but like the atomic model, there's a few things were sort of creeping up in physics, like the black body spectrum of the photon, basically the spectrum of light that a warm body or that a heated body will emit. You can get to that, but it doesn't make sense until you use this sort of accounting idea that Max Planck came up with, and that was fine, right? And then Einstein was actually the one who said, hey, Max, that means that you're saying that light only comes in particles called photons, right? That was all Albert, and it's really strange when you think about that like there's a minimum and multiples of that minimum at every light frequency. There's just these allowed modes, these allowed electrostatic modes. Because I always thought electromagnetism, but geez, it's completely continuous, but that's not true. Einstein figured that out. And then de Broglie and Bohr and others, they started working on the hydrogen atom. And as you know, I'm sure the hydrogen atom has a discrete spectrum, right? If you put hydrogen in a tube and you excite it somehow and you look at the emission spectrum, there's discrete lines, It's not just light, it's, ultraviolet, this one, and they came up with this funny reciprocal law, Rydberg did, but nobody knew what the hell it meant. But so that's kind of where we're beginning now, right? So this is a 27-minute YouTube, so hopefully you guys like it. Don't tell Xiaowei.
It is amazing to think that as recently as the beginning of the 20th century, there
Can you
was
guys
still
hear?
a great deal of debate surrounding the existence of atoms.
Yeah.
Those
Okay.
who doubted their existence
Okay.
cited the simple fact that they could not be directly observed, and therefore how could we possibly conclude that they exist? Whereas those who supported the atomic hypothesis referred to the remarkable success of the kinetic theory of gases, which was able to account for the macroscopic properties of gases by assuming that they were comprised of trillions upon trillions of tiny atoms in random motion. The reason we couldn't see the atoms was simply because they were too small. However, the debate was short-lived. A series of remarkable experimental observations at the beginning of the 20th century could only be explained using the atomic theory. And furthermore, it was realized that the structure of the hypothesized atoms could be used to explain the incredible diversity of the properties of material objects in the natural world. When, in 1897, J.J. Thomson proved by experiment that tiny negatively charged particles called electrons can be extracted from atoms, leaving behind positively charged ions, it became clear that atoms are not, as the Greek meaning of their name implies, indivisible constituents of matter, but rather complex systems formed by positively and negatively charged parts. In 1904, Thomson proposed a model of the atom in which he visualized the atom as being formed by some positively charged substance uniformly distributed throughout the atom, with negatively charged electrons embedded like plums inside a pudding. However, the model was not without its problems. Whilst it was possible to derive some stable configurations of motionless electrons embedded in the positively charged medium, he suspected that it was the motion of electrons inside atoms that was responsible for the properties of magnetic materials. However, his model was incapable of accounting for the motion of electrons within the atom. The experiment that ultimately caused the death blow to the plum pudding model was the famous alpha scattering experiment of Geiger and Marsden in 1909, which involved firing a stream of positively charged alpha particles at a thin piece of gold and measuring the angles of deflection. According to Thomson's model, if you fire high-energy alpha particles at a thin gold leaf, then you should find that practically no alpha particles are reflected by the gold. This is because the diffuse positive charge filling Thomson's atom would provide minimal repulsive force, and therefore be unable to deflect alpha particles back towards the source. However, when Geiger and Marsden performed the alpha scattering experiment, they found that roughly 1 in every 8,000 alpha particles were deflected back towards the source, in direct conflict with Thomson's prediction. In March 1911, Ernest Rutherford proposed a radical new model of the atom in order to account for the experimental results of Geiger and Marsden. According to Rutherford's model, the atom consists of a tiny positively charged nucleus, surrounded by even tinier negatively charged electrons, which occupy the vast regions of space around the nucleus. This explained why most alpha particles pass through the gold leaf, since they are simply passing through the vast regions of empty space within inside the atoms of gold. However, in those rare cases where an alpha particle collides head-on with the gold nucleus, the concentration of positive charge within the nucleus is sufficient to push the alpha particle backwards, and this accounts for the 1 in 8,000 alpha particles that were scattered back towards the source. Although Rutherford's model was a significant improvement over Thomson's, it was plagued with problems of its own. If the electrons are believed to exist in the space surrounding the nucleus, then what exactly are they doing? They can't just be standing still, because the electrostatic force of attraction between the positively charged nucleus and the negatively charged electrons would surely cause the electrons to be pulled into the nucleus, and this would imply that all atoms are inherently unstable and therefore should collapse. The obvious solution to this problem is to propose that the electrons are in fact orbiting the positively charged nucleus, much like the Earth orbits the Sun, and that it's the orbital motion that prevents the electrons from falling into the nucleus, just as the motion of the Earth stops our planet from falling into the Sun. However, the orbiting electron model doesn't work either. To see why, we need to refer to Maxwell's theory of electromagnetism, which had been developed in the second half of the 19th century. According to electromagnetism, surrounding every charged particle there exists an electric field, and if you change the position of a charged particle, then the field will also change. Now, according to electromagnetic theory, if a charged particle moves in a circular orbit, then the acceleration of the particle will cause a ripple in the surrounding electromagnetic field, corresponding to the emission of electromagnetic radiation. If we apply this to an electron orbiting the nucleus, then we see that as the electron orbits the nucleus, it will radiate energy, and therefore as it loses energy, it will slow down and spiral into the nucleus. And electromagnetic theory predicts that this would occur in less than a trillionth of a second. So it appears that the electron cannot be standing still, and it cannot be orbiting the nucleus like a planet orbits the Sun. So what exactly is it doing? The answer to this question would require a union of the old classical ideas of electromagnetism with the newly developed ideas of energy quantization, as put forward by Max Planck and Albert Einstein. And it would require the remarkable vision of one man, Niels Bohr, who would become one of the founding fathers of quantum mechanics. In 1911, after completing his PhD at the University of Copenhagen, a 25-year-old Niels Bohr joined J.J. Thomson at the Cavendish Laboratory in Cambridge with the hope of working with Thomson on the structure of the atom. However, folklore suggests that J.J. Thomson and Bohr's relationship did not get off to the best of starts when, during their first meeting, Bohr apparently entered Thomson's office with a copy of one of Thomson's books on atomic structure, pointed to a particular section and declared, "This is wrong." It is hardly surprising, therefore, that Thomson did not immediately warm to him. A number of disagreements between the two men forced Bohr to abandon Cambridge and head for Manchester, where he had been invited by Rutherford himself. Like Einstein and Planck before him, Bohr realized that attempting to resolve the problems of the atom using purely classical physics was probably doomed to failure. Instead, he should take seriously the idea that energy is only ever transferred discretely in chunks, or quanta, rather than in the continuous fashion predicted by classical physics. Furthermore, Einstein's explanation of the photoelectric effect in 1905 had demonstrated that light should be considered a stream of particles, called photons, each consisting of a discrete amount of energy. Faced with the challenge of the stability of the atom, Bohr took a leap of faith and simply hypothesized that in order for atoms to be stable, there must exist stable configurations of the electrons orbiting the central nucleus, and that these stable orbits should depend, in some as yet unspecified way, on Planck's constant. Furthermore, he suggested that the transitions between these stable states would cause the emission of photons of discrete energy. Young, enthusiastic, and unhampered by the limitations of classical physics, Bohr launched into a period of intense productivity, resulting in the publication of 3 papers in 1913 that would change the landscape of atomic physics forever. Bohr's groundbreaking work focused on the simplest atom, hydrogen, and was based on 4 postulates that combined elements of classical and quantum physics. The first was based on Coulomb's law from classical electrodynamics. According to this postulate, the electron is held in orbit around the nucleus by the Coulomb force of attraction between the positively charged nucleus and the negatively charged electrons. The second postulate is the assertion that, contrary to predictions of electromagnetic theory, the electron does not radiate energy despite the electron's acceleration. The second postulate removes the problem of the stability of an electron by simply postulating that this particular feature of the classical theory is not valid for the case of an atomic electron. This postulate was based on the fact that atoms are observed by experiment to be stable, even though this is not predicted by the classical theory. This may seem like a rather bold assertion, but Bohr was hopeful that the exact mechanism explaining how this is possible would emerge later. The third postulate introduced the idea that the angular momentum of the electron is quantized in units of Planck's constant divided by 2 pi. And the final postulate suggested that photons of light are emitted by atoms whenever an electron moves from a higher energy orbit to a lower energy orbit. The justification of Bohr's postulates, or of any set of postulates, can only be found by comparing the predictions that can be derived from the postulates with the results of experiment. So we will now consider these ideas in a bit more detail. We will begin by looking at the quantization of angular momentum. According to classical physics, the angular momentum of an orbiting electron is found by multiplying the mass of the electron by the vector cross product of the radius and velocity vectors. Furthermore, the magnitude of the vector cross product of any 2 vectors is given by multiplying together the magnitudes of the individual vectors and the sine of the angle between them. In the case of an electron in a circular orbit, this angle is always 90 degrees, and therefore sine of 90 equals 1, and we see that the angular momentum is equal to the mass of the electron times the velocity times the radius. Now, we see from this expression that according to classical physics, because the radius and velocity can vary continuously and take any value, so too can the angular momentum. However, Bohr proposed that the angular momentum of the orbiting electron is quantized in integer multiples of Planck's constant divided by 2 pi. If we combine the classical and quantum expressions for the angular momentum and rearrange for the radius of the electron orbit, we find the following expression. Before we can fully appreciate what this equation is saying, we need to find a way of describing the motion of the electron in its orbit around the nucleus. Bohr assumed that the electron was held in its orbit around the nucleus by the Coulomb force of attraction between the electron and the proton. Coulomb's law states that the magnitude of the force acting between 2 charges Q1 and Q2 is proportional to the product of the charges and inversely proportional to the square of the distance between them. Applying this to the example of a single electron of charge E orbiting a single proton of charge E, the electrostatic force is given by the following expression. Next, we assume that the electron is orbiting in a circular path of radius r with speed v. Because the direction of the electron is constantly changing, the electron must be accelerating, and therefore, according to Newton's second law, there must be a resultant force directed towards the center of the circle that is causing this acceleration. In the case of circular motion, the centripetal acceleration is given by the expression a equals v squared over r, and if we combine this with Newton's second law, we find the following expression for the centripetal force acting on the electron. Bohr assumed that the centripetal force was provided by the Coulomb force of attraction, and therefore he equated these two mathematical expressions to arrive at an equation for v squared. Next, he used the expression derived for the radius using the angular momentum quantization condition. If we square this expression and substitute the blue equation for v squared, we arrive at the following equation, which tells us the radius of the allowed electron orbits. Let's take a closer look at this equation. We see that the electron is only allowed to orbit the nucleus at certain distances, depending on the value of n. If we substitute the appropriate values for Planck's constant, the permittivity of free space, epsilon naught, the mass of the electron, and the charge of the electron into this equation, we find that for n equals 1, the so-called Bohr radius is calculated to be 0.53 times 10 to the minus 10 meters, and this provides a rough estimate for the atomic dimension of the hydrogen atom. When Bohr calculated this value, he was reassured that the value he found on the basis of angular momentum quantization was in line with other known estimates for the size of the atom. If we next calculate the radius of the n equals 2 and n equals 3 orbits, then we see that the distance between adjacent orbits grows as n increases. Another thing that Bohr was able to calculate was the orbital speed of the electrons. Recall that we were able to derive an expression for the speed of the electrons using Coulomb's law. If we then substitute r into this equation, we find the following expression, which can be used to calculate the speed of the electron in different orbits corresponding to n equals 1, n equals 2, and so forth. Clearly, the fastest possible speed will correspond to the innermost orbit when n equals 1. In that case, we find a speed of 2.18 times 10 to the 6 meters per second, which is reassuringly less than the speed of light. And so Bohr was pleased to see that his model of the atom did not appear to violate Einstein's theory of special relativity. Once Bohr had determined the radii of the allowed electron orbits, his next task was to determine the energy of each of these orbits. In order to do this, he realized that the total energy of the electron will simply be the sum of its kinetic energy and potential energy. The kinetic energy is due to the motion of the electron, whereas the potential energy is due to the electrostatic force of attraction between the electron and the positively charged nucleus. Now, the kinetic energy is easy to calculate, as I'm sure you remember from school. It's simply given by half times the mass times the velocity squared. The electric potential energy is derived from Coulomb's law, and for the hydrogen atom is equal to minus E squared over 4 pi epsilon naught r. Why the minus sign? Well, the minus sign is there because the convention in physics is to define the potential energy at infinity to be 0. And since the potential energy of the electron increases as it moves further away from the nucleus, it must be negative for finite separations. So if we add these two equations together and substitute the following expressions for v squared and r, which we derived earlier, then we find the following yellow expression, which simplifies in the following way. Note that all of the terms inside the bracket are constants. If we substitute the experimentally determined values for each of these constants, we find that the combination of terms inside the bracket corresponds to a numerical value of 2.18 times 10 to the minus 18 joules. And so we can write the total energy of the electron as minus 2.18 times 10 to the minus 18 joules divided by n squared. This equation tells us the energy of the electron in each of the allowed orbits corresponding to n equals 1, n equals 2, n equals 3, etc. As you can see from this equation, the orbital energies are very small, and therefore physicists often write the energy using a different system of units called electron volts rather than joules. An electron volt is defined as the energy transferred to an electron when it is accelerated through a potential difference of 1 volt. So for example, imagine you had two parallel conducting plates connected to a 1 volt battery. If you placed a single electron at the negative plate, it would clearly experience a force and accelerate towards the positive plate. And the amount of kinetic energy it gained moving between the plates is what we define as an electron volt's worth of energy. In order to calculate how much energy in joules an electron volt corresponds to, we can make use of the definition of potential difference, which is defined as the energy transferred per unit charge. If we rearrange this equation, we find the energy transferred is equal to VQ. So in the case of an electron with charge E moving through a potential difference of 1 volt, we see that the energy transferred equals 1.6 times 10 to the minus 19 joules. And this is what we call 1 electron volt. So 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. If we now rewrite the total electron energy in electron volts, we find the following famous equation: E equals minus 13.6 over n squared electron volts. And this equation tells us the energy of the nth electron orbit. Now if we calculate the energies of the first 6 orbits, then we find the following values. We see that the energy difference between adjacent orbits decreases as n increases. We can picture these orbits in a number of ways, but it is often convenient and conventional to represent the energy levels as a series of parallel lines with the lowest energy, also known as the ground state energy, at the bottom. As the electron moves away from the ground state, its energy increases, and an infinite distance from the nucleus, the energy is defined as 0. Bohr realized that in order for an electron in the ground state to move to a higher energy state, it would need to absorb just the right amount of energy, corresponding to the exact difference between two energy levels. When an electron moves from a lower to a higher energy level, it is said to be excited. So for example, imagine that an electron is excited from the ground state to the n equals 4 energy level. The question Bohr then asked was, how does the electron lose energy such that it can return to the ground state? It was at this stage that Bohr delivered his master stroke. He realized that the electron loses energy by emitting a photon, and that the energy of the emitted photon is equal to the difference in energy between the higher and lower energy level. The greater the energy difference, the greater the energy of the photon. Bohr also realized that there were often more than one route that an excited electron could take in order to return to the ground state. In our example, we see that the electron could hop between every level on its route to the ground state, or it could move from the n equals 4 to the n equals 3, then the n equals 1 level, or it could move from the n equals 4 to the n equals 2, and then from the n equals 2 to the n equals 1, or it could go straight from the n equals 4 to the n equals 1, and each of these different transitions would correspond to the emission of a photon with a particular amount of energy. Let's now look at this in a bit more detail. Imagine that an electron in the ground state is excited to the n equals 2 energy level. When it de-excites and drops back down to the ground state, it will emit a photon. And as we know, the energy of a photon is given by the equation E equals hf, or E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. We can work out the energy of the emitted photon by calculating the difference in energy between the n equals 2 and n equals 1 level. If we put in the numbers, we see that the energy difference is equal to 13.6 minus 3.4, which is 10.2 electron volts. And if we convert this into joules, we find that the energy difference is 1.63 times 10 to the minus 18 joules. So this is going to be the energy of the emitted photon. We can work out the wavelength of the emitted photon by using the equation lambda equals hc over delta E, and we find that the wavelength turns out to be 122 nanometers. So what kind of photon is this? Well, the wavelength of the photon tells us about the type of radiation emitted. Visible light has a wavelength of between roughly 350 and 750 nanometers, with violet light being at the short wavelength end and red light being at the long wavelength end. Wavelengths slightly longer than 750 nanometers take us into the infrared region, and wavelengths slightly shorter than 350 nanometers take us into the ultraviolet region. And therefore we see that the 122 nanometer photon is an ultraviolet photon. In other words, photons emitted as a result of this particular transition are not directly visible. Likewise, electron transitions from the n equals 3, 4, 5 and 6 energy levels down to the ground state will all cause the emission of ultraviolet photons. This series of wavelengths is referred to as the Lyman series, named after Theodore Lyman, who first discovered them. The natural question to ask at this stage is whether any electron transitions correspond to the emission of visible photons, and the answer is yes. We are going to consider electron transitions from the n equals 3, 4, 5 and 6 energy levels down to the n equals 2 energy level. Let's see what we get. Firstly, if we calculate the wavelength of the photon emitted when an electron moves from the n equals 3 to n equals 2 level, we find a value of 654 nanometers, and we see that this corresponds to a reddish color in the visible spectrum. Next, if we consider a transition from the n equals 4 to n equals 2 levels, we find a photon of wavelength 488 nanometers, and this corresponds to a light blue-green color. The n equals 5 to n equals 2 transition corresponds to a wavelength of 435 nanometers, which is a deep blue color. And finally, the n equals 6 to n equals 2 transition corresponds to a wavelength of 412 nanometers, which is a purple-violet color. And in terms of visible photons, this is it. You can try calculating the photon wavelengths for all other possible transitions within the hydrogen atom, and you will see that these are the only 4 transitions that cause the emission of visible photons. And so rather than having a continuous spectrum of colors, we actually have what is known as a line spectrum, consisting of 4 lines of color. And the wavelengths corresponding to these 4 lines are unique to hydrogen, a bit like an atomic barcode. These 4 visible lines are named the Balmer lines after Johann Balmer, who discovered an empirical equation to predict the Balmer series in 1885. It had long been known that if you pass the white light emitted from a hot object, such as the sun or a filament lamp, through a triangular prism, then the light will disperse and a continuous spectrum of colours will be observed. However, detailed experimental investigations in the 19th century revealed that the light emitted from a glowing gas of a particular element does not form a continuous spectrum. So how do you make a gas glow? Well, that simply involves taking a rarefied gas and passing an electric current through it. Collisions between the electrons flowing through the gas and the atoms of the gas cause the gas to emit light. If you then pass that light through a triangular prism, what do you get? Well, in the case of hydrogen gas, you observe the following pattern. And if we overlay the colours predicted by Bohr's model of the atom, we find remarkable agreement between the colours and wavelengths of light. Note that the purple-violet line cannot be seen in this picture, and this is simply because this particular emission line has a very low intensity, which was not picked up in this particular photograph. One of the remarkable successes of Bohr's model of the atom was its ability to explain the hydrogen emission spectrum. We see that these unique lines are simply a result of electron transitions between discrete energy levels inside the hydrogen atom, and that the discrete energy levels are a consequence of the angular momentum quantization condition. So we see that introducing the quantum into the atom not only helped to stabilize the atom, but also helped to explain the emission spectrum of the hydrogen atom. But it wasn't only the hydrogen atom that could be explained using the Bohr model. The basic idea of energy levels and electron transitions would ultimately account for the emission spectra of all the known elements in the periodic table, and Bohr's model would be hailed as a triumph, for which he would be awarded the Nobel Prize in 1922. As is often the case in physics, the solution to one set of questions naturally gives rise to a new set of questions. Bohr wrote to Rutherford on the 6th of March 1913, enclosing with his letter a manuscript with the title On the Constitution of Atoms and Molecules. In his reply, Rutherford reacted favourably but raised some difficult questions. He was particularly puzzled by the fact that, in Bohr's model, an electron in a high-energy orbit would somehow need to know beforehand the energy of the final destination in order to emit radiation of just the right wavelength. In this simple statement, Rutherford was raising the alarm about the implications of the new quantum theory for our understanding of cause and effect, and this alarm would continue to sound for the remainder of the century and well into the next. The success of the Bohr model, as measured by its agreement with the experiment, was certainly very striking, but it only accentuated the mysterious nature of the postulates on which the model was based. Where did the angular momentum quantization condition come from? And what was the mechanism behind electron transitions between energy levels? The answers to these questions would have to wait nearly a decade, until the beginning of the 1920s, when the pioneering work of de Broglie, Schrödinger, Heisenberg and Dirac would lay the foundations for the most successful theory ever created on Earth, quantum mechanics. Our vision of reality would never be the same again. Reflecting on this fact, Bohr said, "We must be clear that when it comes to atoms, language can be used only as in poetry. The poet, too, is not nearly so concerned with describing facts as with creating images and establishing mental connections. Physics is not about what the world is, it is about what we can say about the world."
Feels
I believe you're muted.
Yeah, I was, yeah.
I unmuted. Thank you. So, so I actually have a couple of, just minor points to talk about this video with, and you guys want to talk first, or you want me to go? Okay, so I'll start, and then we can sort of go from there. But now I'm not really sure if this is true, because the author of the video said that that Bohr proposed that the energy levels were quantized, but certainly in later stuff, like with the Schrödinger equation, the quantization arises from the mathematics. So, and this is also a general point about science and stuff like that. Like when you put together a model of reality, 99.9% of the time, you use what's called a differential equation, right? If you've looked at Newton's laws, like F equals ma, force equals mass times acceleration, that's actually a differential equation, because acceleration is d squared x dt squared, and then force is, shit, I forgot what it is. Anyway, it'll come to me. But Newton's laws are partial differential equations too. And the solutions you come up with them, they come from the boundary conditions you impose, and then the differential nature of the equations that you have. And in quantum mechanics, one of the boundary conditions is that the wave functions have to be periodic. That is, they have to start and end at the same place. So in a circular orbit, if you go around the circle, you have to, if it's say 0, and then it goes -1, -2, -3, -4, -3, -2, -1, and that has to hit 0 again at the same point. That boundary condition creates the need for quantization, and that's where n pops up there. And then you'll recall probably from chemistry that for any atom, you've got 4 quantum numbers, N, L, M sub L, and M sub S, right? And those all come out of the same considerations, right? It's like the partial differential equation, and you work through the solutions and they're quantized because it's the only way you can solve the equation. Anyway, that's a lot of baloney, but I hopefully it will help you at some point. I don't know. So another thing I thought was interesting was how as Bohr was working through this, the same with Schrodinger and everybody else, at least on the solution side, you use classical physics. You use Coulomb's law, that R squared dependence. You know, the force that charges feel is K Q1 Q2 over R squared. You use Coulomb's law, and you also use well, anyway, you definitely use that, and use the inverse square law, right? But I've been talking too much. Who wants to make a comment? Who has a little bit of courage left over to say, I didn't understand this, and say what part of it you don't understand?
Why were the energy levels negative?
I have no idea. I don't really know. Dude, that's a really weird question, right? Because the energy, the way they define it, the energy for separated charges, separated to infinity, is 0, and then it becomes more and more negative as they come together. You know, I hate to say it, I think that's just a convention for how they do it, but it's really strange, huh? And then it's interesting in Bohr's model that they have the kinetic and the potential energy terms there. It's the exact same in the Hamiltonian operator for the Schrodinger equation. Got the potential and the kinetic energy terms, however you want to do them. And it is just so cool that all of the fine structure of the atomic and the molecular spectra and everything come from the addition of other kinetic and potential energy terms into that Hamiltonian. You just have to add them in, and then experiment and theory agree. It's just wild. So, for example, how many of you believe this bullshit that there's no such thing as a vacuum?
Isn't that just
You know,
not
like,
true? Haven't people made vacuums before?
oh yeah. Yeah, you could make a vacuum, you can make a nice high vacuum, right? But the reason that people doubt that is because of splitting in the hydrogen atomic emission spectrum. And so like, say, what the bleep are you talking about, Dr. Taro? You big jackass, right? But it just blows my mind because, like, there's this guy physicist named Lamb, and he discovered what they call the Lamb shift, right? And it's just LAMB. You can look him up, right? And all these physicists, literally, they were on a train. They were going to a conference, and they were talking on the train. And they're saying, I don't understand this, you know, there's, they were refining the Schrodinger equation for a hydrogen atom, and it just wasn't coming out right. There was a difference in some of the energy levels, and it was just like, what's it? And it's just a tiny difference, And Lamb said, oh, well, the uncertainty principle thing? Well, it says that you can't have a real vacuum because then the energy is zero and the momentum zero, and that doesn't make sense, right? And everybody's like, shut the bleep up, Lamb. We're going to eat you for dinner, But he was right. And he proved it. He did basic calculations on the refractive index of a medium with positive and negative energy particles that pop into existence and then annihilate, and pop into existence and annihilate. And that is called vacuum energy. And it works exactly to explain the Lamb shift in the hydrogen spectrum. And that is when you get true believers, because nobody could explain it until this crazy guy named Lamb came along. He said, oh, no, it's because you can't have a true vacuum, right?
So wait, vacuum energy is a real thing, or?
Yeah, it's very real. Very
Wait,
real. I mean, it's a, yeah,
I'm
go
just
ahead.
gonna say,
Go
can you
ahead.
please describe it again so I could write it down?
I can't, I'm sorry. I'm gonna try. I'll try. So there's so I can tell the story of the Lamb shift, right? Which is that when you go through and you calculate the positions, the exact positions of the energy levels of the emission spectrum of hydrogen, right? You have to have the kinetic and the potential energy terms right? And it turns out there are others. There are magnetic terms that come from the electrons interacting, and then the magnetic moments of those electrons in the orbits, right? So there's spin and there's orbit, and there's all these little terms, right? And they were getting them. They were almost there, right? But some of them just weren't right, and they could not figure it out until Lamb came up with the idea, or he invoked the idea of the vacuum energy, right? Of the vacuum containing positive and negative. It's literally displacements from positive and negative energy, so that the vacuum can obey the Heisenberg uncertainty principle, right? That you can't know the energy and momentum of the vacuum, whatever that means, exactly simultaneously, right? So Lamb computed the effect that energy has on the refractive index of a vacuum as experienced by an electron doing its thing, right? And it came out exactly right to make experiment meet theory, right? And so he could have, and this is a case that's happened over and over in quantum mechanics, is that the theory is way ahead of the experiments. In that case, they were just neck and neck, right? The theory was there, the experiment, and then they agreed, right? But there are many other examples where the theory was way ahead of the experiments, way ahead. And we'll talk about them more when I remember them. I hope I can remember them. But there are other examples. Yeah, like the existence of spin, for example, the electron spin. Like what is spin? Who knows? But you know, but it was predicted, it is predicted by Dirac's theory of the electron. You know, Dirac was working on the electron and he just couldn't get it. It just did not work because there's like this symmetry problem with when you multiplying numbers and things would get all messed up, right? So I said, well, the only way to do this is if instead of numbers, these quantities that I'm trying to multiply are actually like tensors or something like that, these multi-dimensional, like these, they're 4 numbers instead of 1, right? Then you could get the proper answers out, right? Plus and minus and everything sort of balanced. Oh, wow, they must be tensors or some shit like that, right? And it turns out that when you do that, you get the right answer, but you also get a negative energy answer. Like you get spin, for one thing. Nobody knew what the hell it was, but then they measured it. Sure enough, and there it is. And then you also get a whole negative energy answer. And Dirac struggled like crazy with that until somebody observed later the anti-electron, the antimatter equivalent of the electron. And that was observed in a particle physics experiment. Yeah. And there it was. Everything worked. And so it's like the math gets ahead of the experiment somehow. I just absolutely love that. And that happens with Maxwell's equations too. And people get all a flutter like I am. Anyway, so let's see here. Oh, and then the last thing I wanted to say about this topic is, oh, by the way, there's Dirac, right? Dirac is here. He, Werner Heisenberg, Paul Dirac, and Erwin Schrödinger, they sort of carried the ball for quantum physics after, you know, Bohr was still around. Einstein was working on a geometric explanation of everything. But Rutherford asked Niels Bohr, he said, well, you know, if an electron drops down and it creates a photon, how does it know where it's going? Like, how can it have the right amount of energy, right? And to me, that's a real subtle question, like, but there is a way that was put into very stark relief for me. And it has to do with a method I was studying called XAFS, X-ray absorbance fine structure spectroscopy. Yeah, you know XAFS, Davida? So XAFS is where when you tune an X-ray to the absorption spectrum of the core electron, then it's just like in a hydrogen atom, but you're talking about normally heavier atoms, right? And you tune the X-ray energy, and then suddenly it'll shoot up. Let me share my stupid damn document. Here we go.
Where did you do XAFS?
Can you guys see? I did not do it. I was just studying it. I actually did some XAFS once at Slack, and then Abe was kind enough to do a bunch of carbon materials for me, but I never did anything with it. I feel so embarrassed. But anyway, but think about this. Think about this. So in XAFs, it's X-ray absorption, extended X-ray absorption fine structure spectroscopy, and it explains how if you look at X-ray energy versus absorption, the number of photons that are absorbed by a molecule, or an atom rather, you can come along and then, boom, the absorbances look like this, right? And what this really is a combination of it's a combination of a couple of effects, right? One is just the X-ray absorption, which is like that, plus the extended absorption, which is like that, right? And the period tau there, the period of this is related to the backscatterers in the environment of the atom that's absorbing. So you have an atom here, and maybe you have a nitrogen, a nitrogen, a nitrogen, nitrogen. They're all at the same, maybe there's a nitrogen front and back. So you got this octahedral scattering environment around a center, right? And the X-ray comes in, and it ejects an electron, right? And the electron, it does not behave like a particle. It behaves like an electron wave. And that wave has amplitude maxima and minima, and they expand away from that center, and they scatter off of those nitrogen atoms, right? So the electron wave front, oops, oh, wait, you guys can't see this, damn it. How come you're not screaming? Sorry. Oh no, this is bad news. I'm talking to Dare. Okay, so you guys are paying attention. So right, here's an atom. Here's an atom coordinated by a bunch of nitrogens, right? And then an X-ray comes in, and then it's gonna scare an electron wave off. Oops, that's not working. Maybe this one will work. It'll scare this electron wave off, right? Right? That electron, when the X-ray comes in, it dumps the energy into the electron. The electron overcomes the binding energy, and then it leaves with a wavelength. And that wavelength, and as a wave, it can scatter then back off of these guys, off of these. Oops. The wave leaves and it backscatters off of the coordinating atoms, right? And then that shows up as this oscillation. That shows up as this oscillation in the absorption coefficient, right? And the wavelength there is a period of the distance, is a function of the distances of the scatterers. right? So you can tell how distant the scatterers are off of from the core that's emitting the electron by looking at the period of oscillation in the X-ray absorbance spectrum, right? It's kind of all kind of fascinating and weird and a little bit complex, but there's a really weird thing about it, right? Which is, how does the electron know when it absorbs a photon if once it has absorbed a photon and is flying away, it will be backscattering with itself constructively? Because all three of those points, every peak in that corresponds to the constructive interference of an electron wavefront with itself as it's leaving the atom. Right, Ximing?
Yeah.
Yes. Good answer. I like that answer.
So that's why like the metallic foil, it will have a lot of oscillation like this. But if the structure is not that altered, it might not have very much.
Right. Yeah, exactly. Although you'll be surprised, Ximing, because this is an excellent way to study glasses. So, if you want to study a solid, sometimes you can use X-rays and get a diffraction pattern. If you have the same structure and the same orientation repeating over and over, that'll diffract X-rays beautifully. But if it's glassy and things are very amorphous, then sometimes you have to do X-ray absorbance, fine structure. And and it works in surprising ways anyway. But so I have bored the crap out of some of you. Hopefully I have seeded your imaginations just a little bit. Now, I want to take just a couple moments at the end here and ask, does anybody have any questions? And I may answer them now or next time. And again, I ask you to be rude, and I ask you to be courageous, and let me know at what point my explanation went off the rails, like you could just say,
I think so. I'm just generally confused about the topic because I've never heard about this. So
absolutely understood. There's always a lot of sort of meta information, in what I'm trying to talk about. And in this case, the whole point of me talking about this is to talk about this question of cause and effect, right? Because, what I'm saying here is that an electron, in order to have a higher absorption coefficient for X-rays, X-ray comes in, kicks the electron wave out, right? That electron has to know before it's absorbed if its wave function after it's ejected will be constructive with itself. Right? It's because that is when it hits a peak, and then there's a valley when the when the outgoing wave and the backscattered wave interact destructively. You know, constructive is when they both have peaks at the same place and valleys at the same place. And
Right.
destructive is when one is peaking and the other one's valleying, right? And this is just a great example of that, I think, because the events of absorption and then this backscattering, they seem disconnected, but they're not. They're all one thing. Like the electron goes in, interacts with the core, and then the electron, or no, it's the X-ray goes in, interacts with the core electron, the electron absorbs the radiation, it leaves, it backscatters off the coordination sphere, it comes back in, and all of those are taken into account in determining the original extinction or the original absorption coefficient of the electron. And so that just, I don't know, that was a case where, you know, I was like studying that and I was like, what? How is that possible? And then I thought, well, that's what they've been trying to tell me. That's what they've been trying to tell you, Roger. You know? All right. Oh, I see. You know, okay, chat came in. Okay. All right. Okay, I'm going to read this comment here. Hopefully it makes some sense. Okay. Okay, so Alicia has an interesting comment on the question of negative energy in the electron energy being negative when it's in the nucleus and yeah, right. And so I don't know, it seems like your explanation, Alicia, is it's saying that there has to be, I'm trying to find you. Hi, Alicia. Hi. It's saying that like it's almost like saying you're saying it's not a convention because this is the convention, right? Because in order to, like you're saying that, and I could be wrong. I could not be getting you here, right? But that if you take a proton and just a hydrogen atom, right, and then you separate them to infinity, say that is the zero energy state, the zero Coulomb energy, right? And then as it comes in, the energy becomes more and more negative, right? And that makes sense. I mean that you know, because you know that energy, it's the system energy is decreasing, right? The amount of energy that the electron and the proton have together is decreasing. And ideally the electron has somewhere to, the electron and proton together have somewhere to put that energy, you know, because if the electron is coming in, it's actually another one of the rules is that in order for something to happen, there has to be a way, a place for the energy to go, right? And it's a funny thing. It's almost like why an alpha particle can fly through gold, because all the possible interactions that it could be having, it's not really having them because there's no place to put the energy for those, And then when it finally interacts with something, okay, I can put my energy here. Whoa, you know. Anyway, I'm getting too excited. Stop it, Alicia. All right, to Chris. Okay, thank you, everybody. And I think that's, you guys have been awesome. Thank you for your courage. Thank you for staying awake. Enjoy the rest of your day. And we'll do more and better tomorrow, I promise.
Thank you very much. Have
Thank
a
you so
great
much. Bye.
Bye.
Have a good one.
Thank you. Thank you so
Bye,
much.
thank you.
Thank you so much. Bye.
Hi, Roger.
Hey, Kiming.
Can I
Yes, sir.
use like 20 or 30 minutes tomorrow afternoon? I just want to teach them how to
Sure.
use a VPN to get access to the library.
Absolutely. Absolutely. So tomorrow I will teach from 1:30 to 2:30 then, right?
Oh, to 2:30? Oh,
Or 1:30 to 3 maybe.
yeah, it's fine. Yeah.
Because 1:30 to 3 and then you can take the last half hour and do the VPN.
Yeah. That would be good.
Okay.
Okay.
Perfect.
Thank you so much.
Perfect. Excellent. Thank you so much. How did the video work? Was that okay? Or?
Yeah, I think it's good.
Yeah, I think it's good to kind of break it up a little bit, you know?
Yeah, definitely. It's I think it's
Yeah.
more relaxing too.
Oh yeah, I know. It
Every
is
day
so intense.
they got so many information and a new knowledge for.
I know. I feel bad for him.
That's crazy.
Oh God. Oh my gosh.
All right. So take a
All righty,
rest.
sir.
Yeah.
All righty. Good. We will see y'all
See you
tomorrow.
tomorrow. Thank you so much.
Bye. Thank you.
Bye.